Today I'm going to talk about the paper examining the rhetorical capacities of neural language models. This is a student presentation at Vector Institute NLP Symposium. Nowadays, smart assistants play increasingly important parts in our daily lives. We interact with them by discourse, and the key components they use to understand the discourse is neural language models. Let's look at an example. If you ask a question to a smart assistant, for example, hey, show me how you dance. The smart assistant uses neural language models to convert this sentence into some formats that it is understandable and processable by the computers. Now, after the processing, the computers gives them a result and it converts the result into a sentence that is understandable by human using the neural language model again. The fact that they can do this conversion indicates that neural language models have rhetorical capacities. This is the ability that we want to access. The fact that they can do this conversion indicates that neural language models have rhetorical capacities. This ability is what we want to assess in this project. Traditionally, the evaluation towards neural language models is done by a score called perplexity. This is a single score, and it evaluates basically everything. But from this score, we do not know the detailed performance of each of these tasks. For example, does the model perform very well on syntax and grammar? Does it handle the discourse structure well? Is it able to recognize the rhetorical signals, or does it have context awareness? We do not know, except that we only know a score of whether it is high or low. In this project, we propose to use handcraft as collection of rhetorical features. This gives us multiple scores. What do we evaluate? We do not care about syntax and grammar for the rhetorical features because they are already pretty well exploited in previous literature. Instead, we look at the three other categories: discourse structure, rhetorical signals, and context awareness. To construct these rhetorical features, we use a framework called rhetorical structure theory. In RST, each passage is organized into a tree format. Each sentence or discourse unit is a leaf in the tree, and each node in the tree is a relation signal. For example, elaboration, contrast, and joint. Each signal connects two children. Usually, if there is one that is more important and one less important, then the more important one is called nucleus, and the less important one is called satellite. But there are some situations where both children are equally important. In this case, we denote them, both of them, with nucleus, as we can see from the contrast and joint relations here. In this project, we develop a structural probe diagnostic classifier. This is similar to a thermometer, but what inputs to this probe is the representations of neural language models. And the output is 4 difficulty scores: signal detection, tree reconstruction, discourse unit detection, and overall score. We use our version of self-attention so that this probe is contains very few parameters and have very specific ability. Please see our paper for details of the probe. If the language model is more capable of rhetorical capacities, it forms better representations of the paragraphs. So we can see lower difficulty scores when we try to probe those rhetorical features. For data, we use two datasets. RST-Probe contains 380 news articles with annotations given by human experts. IMDb contains 50,000 movie reviews with their labels given by a parser. As we can see from this histogram, the relative frequency of rhetorical signals are pretty similar, with elaboration, joint, and attribution the most frequent signals. However, each article contains, in RST-DT, contains more signals than IMDb. This is because RST-DT articles are usually longer. We found that contextualized language models outperform word embeddings. Traditionally, the word embeddings map words into fixed-length vectors, regardless of where those words occur in. However, contextualized language models consider the previous and afterwards context. So it is understandable that contextualized LLMs, including BERT, GPT-2, and Roberta, contain easier to decode rhetorical signals than word embeddings like GloVec, fast-text, and random embedding. As we can see from this plot, except from GPT-2, all other contextualized language models significantly outperform the word embeddings on these tasks. What can we learn from this project? This project gives us some hints about what the next generations of smart assistants should be. Neural language models empower better smart assistants of the next generation because they are able to handle massive data and incorporate knowledge from the corpus that was not able to be encoded in previous generation models. And neural language models are widely used in different tasks like question answer, grammar correction, chatbot, and summarization. We need deep contextualized neural language models. And depending on the task we are using, we need careful evaluations about the capacities in the custom use cases. Come chat with us at poster 19 at 12 p.m. to 12:30.